Hello guys, welcome to the tutorial for linked list operations. I am Anuj Dhawan. So first of all, let's begin with an outline for the lecture. We'll start with having an introduction to linked lists, and then we'll see how to represent different nodes in linked list. Then we'll go on with having an overview of different operations that we can perform, and then we'll go on having a detailed view of the important operations, particularly insertion, deletion, and finding a node with a particular value in the given linked list. Finally, we'll have a look at important practice questions. So first of all, what is a linked list? A linked list is a linear data structure that consists of a series of connected nodes. So as we can see in the diagram, we can see that there are different nodes and they are interconnected by links. And as it is evident from the diagram that each node will have a field for representing the data and a field for representing the pointer to the next node, as we can see from this diagram. So the importance of this link is that by having just a pointer to a single node in the linked list, we can rather traverse the entire linked list. So let's understand this with the help of an example from the diagram itself. So suppose we have a pointer to the first node in this linked list, which is labeled as 1. So if we have let us call this as the head pointer. So if we have this head pointer with us, we can move to head next and we can reach the second node. And if I move head next, then I can reach the third node, and so on. So therefore, this next pointer will help us traverse the entire linked list, and at the same time just keeping track of a single pointer to represent the entire linked list. So therefore, this next pointer is quite important. And let's have a look at important terminology, which is, first of all, there's a head pointer in a linked list, which, as we discussed in the diagram, points to the first node in the linked list. And as we can see that the last node's next pointer will actually point to null. So null is a special field in many programming languages. So how to represent a node in of a particular linked list? So we have written a pseudocode of C language, which will help you get an idea about how to code the structure for linked list. So largely you need two fields to represent this node. First of all is the information that that particular node is supposed to carry, and apart from that, the second field will be the next pointer. So let us maybe discuss an example, a real life example. Maybe like we can think of a train with a number of different bogies. So in that particular case, we can represent each bogie as a node of the linked list, and the links of different bogies will be modeled as the next pointers in the particular structure. So the information in each particular bogie can pertain to its capacity, can pertain to the kind of things that it carries, or largely depends on the application for which we are designing the linked list. So before we begin with the linked list operations, so let's first of all have a large discussion on why we actually need linked lists. Because as we discussed, that linked list is a linear data structure, and we already know a linear data structure, which are arrays. So what was the need that we needed to design another linear data structure, given that we already had arrays? So as we would all have worked with arrays and realized that, for example, I have an array containing 1, 2, 3 and 4. And let us suppose that I need to insert 2.5 between 2 and 3. So for that, since array is a quite kind of a rigid data structure, so it does not provide you with an option that you can insert something in between. So the only option that arrays will provide you is that you insert 2.5 in place of 3, and then you insert 3 in place of 4, and you and if there is a space for another element at the end of the array, then you can insert 4 at the end of the array. So therefore insertion appears to be an order n operation in array. So similar thing holds for deletion. So therefore what we realize is that arrays are quite rigid in that particular sense, but when we come to linked list, we'll realize that linked lists are rather quite dynamic, and operations like insertion, deletion, and basically changing the structure of that particular linked list is quite an easy operation as compared to arrays, where it is rather an expensive operation. So these are the reasons that we rather developed another linear data structure, namely the linked lists. So let us have a look at the important operations of the linked list, and simultaneously I'll try to bring a contrast with arrays, that if you want to do the similar operation in arrays, then what would be the time complexity for it, what would be the space complexity for it, and which of the two data structures fares better in for each of these particular operations. And as we can clearly see, the operations that we have picked up fairly general enough, and for whatever application you design the data structure, you will get across these operations often. So therefore these are the operation, and in general that's a principle for data structure design in general, that whenever you are deciding which data structure to choose, first of all you need to get an idea about which kind of operations are going to be regularly performed in that particular data structure, and based on which data structure basically performs those operations quickly, you need to make your choice. So therefore it's really important that whenever we are studying any data structure, we need to thoroughly know about how it performs the standard operations, in what time complexity, in what space complexity, since this is the knowledge that will help us to choose between different data structures when we actually have to choose that in practice. So the three operations that I'll be discussing in detail in this lecture are insertion, deletion, and searching for a node of a particular value in the linked list. So as you can see that we have tried to divide these each operation in a number of special cases. For example, for insertion, insertion at the first, at the middle, at the end. And as we proceed further, you'll realize that why have we done so. Okay, so first of all, let's begin with the first operation, that is insertion of a particular node in a linked list. So instead of writing up a general code, I'll move case by case, because that will help you get an idea about how we need to rather be careful about coding, especially with pointers. Because in general, whenever we are coding with pointers, there are a lot of different small points that you need to be sure of, and that small invariance that you need to maintain while doing different operations. And so let's begin with insertion in an empty list. So as we discussed earlier, if you want to represent a linked list, so a linked list would be represented by a head node. But in this case, the list is empty. So first of all, like whenever we want to insert a particular node in a linked list, we first of all need to allocate space for that particular node. So the first in general, for any kind of insertion, since we always need to allocate new space for that particular node, so first operation that we'll largely be doing is allocating space for that particular node, which malloc does us for in C programming language, and we have similar operators, for example new in C++, for allocating spaces. So throughout this example, throughout this lecture, we'll actually be following C language, and the code and the concepts are largely similar for other programming languages as well. So in the first line, we try to allocate space for this particular node, and then as we discussed, there are two fields for in a node structure, that is data and next. So we need to set both of them. So data will actually point to the value for which I actually want to insert, for the value which actually want to insert in the linked list, and the next for now points to null. Now, since the linked list is empty, so I'm actually creating a list after while I'm inserting the first node. So the head of the linked list will always point to the first node in the linked list. So as you insert this new node, it will automatically become the head of the linked list. So we need to do that operation, and the last operation tells us that we actually setting the value of the head pointer to the node that we actually just created. And this diagram will actually help you get an idea about the operations. So the next operation that we'll be working upon is insertion. So insertion at the front of the linked list. So okay, before we proceed further, an important concept or important rider that I want to tell all of you is that whenever we are working with linked lists, always be sure that your head pointer always points to the correct node, because head pointer, as we discussed, is the key to the entire linked list. So whenever you're trying to delete a node, insert a node, or search a particular node, be sure that the head always points to the correct value. Since if the access to the head pointer is lost, then we'll actually lose the access to the entire linked list. So in each of the case, I'll be explicitly discussing about what's the status of head pointer in that particular operation. So as now, let's come back to what we were discussing before, that is insertion at the front of the linked list. So coming to insertion at the front of the linked list, because since it's an insertion, we need to allocate new space for the linked list. So we'll first of all allocate that space using malloc, and then we'll actually set the particular pointers values. And apart after that, see the next, if we compare with the previous and this case, we actually see the difference is just in this particular operation, that earlier with the new node that I was creating, I was setting its next value as null, but now there's an entire list which is standing behind this particular node, so its next pointer will point to the head. And after I insert this, the head now should become this new node, because as you can see in this diagram, the head, since it points to the first node in the linked list, becomes now the new node that we have inserted. So head actually points to the new node. The next is actually insertion at the middle of the linked list, which is a purely general case. And it's an exercise for you that try to extend this particular code for insertion at the middle of the list to insertion at the front and insertion at the last by using if and else constructs. So that would be really a really interesting exercise for you, and will sharpen your skills on the pointers. So, okay. So as we were discussing, insertion at the middle of the list. So before just starting to code, it's always a suggestion that for working with pointers, try to visualize what's all happening. Try to understand what operations you need to perform, and writing the code would be fairly simple. It's just a 4-line code in this case also. So let's understand this with an example. So let us suppose that the original linked list that we had was 10, 20, 40, and 50 in this order, and we wanted to insert the 30 value node between 20 and 40. So let's figure this out from this diagram only. So what all do we need to do? We need to first of all set the next pointer of 20 pointing to 30. That's the new node. Then we need to set the 30's next pointer pointing to 40, and we are done. So let's that we actually did for this particular example. So let's try to generalize this before we can actually code up. So for insertion in the middle, we always need to, in the question be given the point where we need to insert. So let us suppose that the question gives us the pointer to the node after which I want to insert the new node, which would be 20 in this case. So let us suppose that prev node be the pointer that we actually get, which points to the node after which the insertion needs to be done. So we have prev node with us, and we need to insert the new node after prev. So first important factor that you will actually that you should actually now think is that if I change the next pointer of this prev node, then after that I'll actually lose hold of this entire list which was after the prev node, because I won't have any access to it. So that is usually the common mistake that people who actually start coding with pointers do, that they'll actually often lose access to left pointers. And this is something that you need to avoid at all costs. So therefore, let's play a trick in this particular case, that rather than setting the value of this prev node's next pointer first, I set the value of new node's next pointer, because new node's next pointer will then be my access point to the entire linked list later after this prev node. So what we do is that we set the new node's next pointer as prev node's next pointer as the first operation that we do. As we can clearly see in this third line, we are doing new node's next is prev node's next. And after I do this, I can safely do new node. After that, I can safely do that prev node's next is actually new node, and we are done. So it might appear some counterintuitive kind of operations to you. So always refer to the diagram. Always try to draw these operations with the help of these boxes and arrows on a paper, and they always come handy and they always are useful. So let's move to the third special case, that is insertion at the last of the linked list. So it's really actually quite similar to insertion at the middle, but all we have to do is that we do not have a trailing list after prev node. So what we actually do is just we do prev nodes next as the new node. Obviously, first of all, we have to create the new node and allocate space for it. That's a general operation for any insertion. But the real game is actually playing with these pointers that are actually usually the last 2-3 lines in all the cases. So here in this case, we just need to set the prev nodes next as new node, and we are done, because we do not have any list further. So this is rather a fairly simple case. So before beginning to deletion, I'll actually suggest all of you to just compare and contrast all these cases, and you'll realize that what's the reason that we have segregated them into these 3 or 4 special cases, and try to code them yourselves. Until unless you code and then test your code on a number of test cases, it's basically learning by doing. After only you code with pointers, you actually become comfortable with it. So before moving to the next operation, I'll actually suggest all of you to pause the video at this particular point and open your editors code up insertion and work on with certain examples, and after you're comfortable with insertion, move to deletion. So okay, so let's start with deletion of a node in a linked list. So after we have done insertion, so deletion is something that you should actually try to think yourselves and try to think along with me, because it should be rather simple after you have learned and practiced insertion. So first of all, insertion at the first of all, deletion of the first or the header node of the linked list. So okay, so when we are deleting a particular node, we actually don't have to explicitly delete it. The thing that in by deletion I mean is that just lose access to this particular node. Just ignore that node. Deletion effectively means ignoring. Just ignore this particular node and make sure that rest all your system is consistent. And after ignoring this particular node, and if it's consistent, then we are done. Because if we do not have an access to that particular node, it's equivalent to being deleted, since we can never use that particular node. So that is the technique or the line of thought that we'll be following in deletion. So first of all, if you want to delete the first node of a linked list, so we already have the head pointer with us. We just need to set the pointer or the value of head as heads next, and just carefully see that we are done. Just a single line code for deletion of the entire node, and rather that's the beauty of the linked list. That insertion, deletion, they just happen after just playing with pointers and just changing one or two pointers. You have inserted at anywhere in the linked list, you have deleted at anywhere in the linked list. Whereas comparing to arrays, you actually need to just transfer each and every point ahead or before, and they are simply linear time complexity operations. But in linked list, they are just constant time operations. That is the region where linked lists actually lead with respect to arrays. So the first deleting of the first node is actually a fairly simple one-line code. So let's move to deletion at the middle of the node, the middle node, deleting a middle node of the list. So let us suppose that we have been given access to the prev node, that is the node after which the node which is just behind the node to be deleted. So let us suppose that we have been given access to the prev node. And in this particular example, let us suppose nth node was to be deleted, and we have been given access to n minus 1th node. So prev node points to n minus 1th node, current node points to the nth node. So in this particular case, as it's quite clear from the example, we just need to do prev nodes next as current nodes next. And we are done again, because whenever now we start traversing, because remember that after this operation, we'll always be having just a head pointer with us. And whenever we start with the head pointer, we move to 10, we move to 20, and now from 20 we move to 40. We never in any way reach 30. So 30 is effectively deleted. So again, a single line code for deletion at the middle of the node, deletion of the middle node of the list. Now coming to the third case, that is deletion of the last node of the list. So it again is quite simple, and just we need to prev node effectively in this case will point to, in this example, it points to 40. So we just do prev nodes next as null, because after 50 there is no node. Just we need to ensure that there is null. So this rather actually completes deletion at the last node of the list. So what I've seen, especially in beginners, is that they do not consider explicitly setting null as an important operation. They feel that even if you do not set as a particular pointer's value as null, then it will be okay, which is not. You need to explicitly set null the pointers which have to be null, or otherwise, as you yourself practice, that will actually run up in errors. And at many times, for example, if you're traversing a linked list, checking that whether you have reached the end of the linked list is checking that whether if you have reached the end of the linked list or not is only possible if you can compare it with a null pointer. So null is quite important, and always be sure that whenever there's nothing that the 40 is next to point to, then it should point to null, and it has to point to null. There's no other option. So do not try to run from these particular operations. So after that, we move to the third operation, the last operation of this particular lecture, that is finding a node with certain value in the linked list. So it effectively means traversing the linked list, because as we traverse the linked list, we just keep on comparing the values of each particular node, and once we reach the desired value, we just break. So effectively, the question or this operation will tell you how an approach to rather traverse the linked list, and it is rather the simplest of all the three operations. First of all, just start with okay. So there's a cache again. So as you see that we have actually used another variable temporary, and which we actually using for traversing the linked list. So what if you do not want to use temporary? We directly work with head because we already have a variable which points to the first node of the linked list. So just think for 1 minute that what can be the case that we have actually had to use this separate new pointer. You have the code in front of you. Just try to think. You can pause the video, think, and because I'll be just telling you the answer just now. Okay, so let's hope that all of you thought the answer, because the answer is that if we directly work with head a variable instead of using another variable, then as we can see that we are moving temp is temp dot next, and in case it was head, then we would actually have kept on changing the value of head as we traverse the linked list. And after that, what we realize is that as I was first time only when I changed the value of the head, the access to the first node is lost. And when we traverse next, the access to the next node is lost. The first advice that I gave to you before starting the operations was that never play with head pointer unnecessarily. Always ensure this invariant that the head pointer points to the first node in the linked list. So that's the reason for this particular case also. So you'll have to need to have another pointer with you for traversal. You can't just simply use the head variable for this traversal. So okay, so the code is rather fairly simple. I'll just read out the code for you. That first of all, we initialize the temp pointer as head, and while temp is not null, as we just discussed, this is actually a standard condition for checking that whether we have reached the linked list, the end of the linked list or not. So while the temp is not null, keep on traversing the linked list. That means keep on setting the value of temp as temps next, and after that, when as soon as you reach the desired value, just break and you return temp. So what if there is no node with that particular value in the linked list? For example, the linked list is 10, 20, and 30, and you need to search for 25 value. There is no node with 25 value. So what will this program return in that particular case? So as we clearly see from this code that it will keep on traversing the linked list until either it gets the desired value, which will not be in this particular example that we are discussing. So what will the termination condition in that particular case? And as it moves forward and forward, temp will now point to null after it reaches the end of the linked list, and this while loop will terminate. So if we have not got the node of the desired value in the linked list, our function will return null. So if, for example, you're using this as a function, so you can also not only use this function as finding a node with a certain value, you can rather use this function also to check if a node is there in the linked list or not. A node with a particular value exists in this linked list or not. Because if it does not, then your function will return null, and if it does exist, your pointer will return a non-null value. Rather, we know that it actually does not return any non-null value. It actually returns the node with that particular value. So it actually, this function will actually do two functions. It will also check whether a node with a particular value is present in the linked list or not, and it also, in the case it exists, it will actually give us the access to that particular node. So let's move to some practice questions, um, important practice questions. So these are the two questions that we have: reversing the linked list and merging two sorted linked lists. So I have picked these two questions very strategically so that you actually learn to code and play with pointers, because both of these operations beautifully help you utilize the skills and knowledge that you have gained from the previous discussions on the three important operations, and it would really be a good point for you to apply your knowledge. So actually I have rather coded up the solutions, and I would actually suggest all of you to those who are actually for the viewers to rather pause the video at this particular stage and try to think about try to think yourselves how to approach this question, and after that only view this last section, because then only you will actually gain something from this particular practice session. Okay, so let's hope that all of you have had your thought of how to proceed in this particular operations. So we'll first of all start with reversing the linked list. So in reversing the linked list, what actually happens is that this is the code for reversing the linked list. So actually what we do is that we actually let's first of all discuss the function signature. We'll actually just accept the linked list, that is just the head of the linked list, and but largely let me give you a very broad hint, and I'll leave the implementation to you rather. So, but broadly, what you need to actually do is that instead of for arrays, what we actually did was we swapped the data of each particular node. But now we are in linked list. So in linked list, we can actually change the structure, and always rather prefer playing with pointers rather than playing with the data, because what happens is that maybe the data that each particular node carries might be in gigabytes. So just transferring or even swapping the data of two nodes will actually be a really expensive operation, whereas just setting one or two pointers values which are always of a constant size is really a constant time operation. So to the largest extent, try to avoid tampering the data values and always play with the next pointers. This is a suggestion that you should always remember while attempting linked list operations. So in this particular case, what you will actually realize is that you just need to maintain three pointers: the previous node, the current node, and the next node while traversing the linked list. And whenever you are at a particular point, for example, 2. So see, let me just give an example. Like we have 1, and then we have 2, and then we have 3. So let us suppose that we reach the current node as 2, and one's pointer has been correctly placed to previous node. And now current node points to 2. But all we need to do is we need to do the current nodes next. Before that, previous points to 1, current points to 2, and next points to 3 in this particular point of the loop. So what we need to do is we just need to change the current pointers next to the previous pointer, and I make this as the previous, I make this as the current, and maybe it was 4 after there, and then we make 4 as the current. So and just move. So this is rather quite simple operation, and after that we realize we actually have accomplished reversal, and reversal can be done in a linear fashion very easily, irrespective of the size of data that each particular node carries. It's a very beautiful play of pointers. So I'll suggest all of you to rather code this solution yourself till the end. We'll actually be posting these solutions in the comment section of the video. So just after that you have attempted the questions yourself, you can actually verify and verify your solutions and have a look at our solutions as well. So let's move to the next operation, that is merging two sorted linked lists. So let me first of all explain this question to you, since the title of the question might not be that much clear. So what we have is we have two sorted lists. For example, we have 1, 3, and 5, and then we have 2, 4, and 6. So let us suppose these are the two linked lists that we have. So these are given in the sorted order. So what I'll expect from you is that you merge these two linked lists such that the final linked list is also a sorted linked list. So in this particular case, it would be 5 and it would be 6. This is what, if these two are the inputs, then what I'll expect this to be the output. Let this be the input, and this has to be the output. This is all I'll expect. So I'll just try to give a very slight direction to you, so that, because this is really a golden question for you for practicing. So I won't rather destroy the joy of attempting it yourself. So I just try to give a very brief, a very large direction rather to this particular question before we start thinking. So what actually you need to realize is that yeah, merging the linked list is obviously a very easy operation if we start creating duplicates of the nodes. For example, I have 1, I have 2, I just create a 1 node, then I create a 2 new node, then I create a 3 new node, then I create a 4 new node, and so on. So that will always be an easier thing for us to do. But we never make use of the fact that we're working with linked lists, not arrays. So we need to again avoid the data intensive and time intensive operations. So the good thing would be that if we can actually do it in constant space, that is, we do not allocate new node, we do not create even a single new node in this entire operation, and we get this new linked list. So that is actually what you need to think at. So a major hint for this particular question would be that you just need to maintain a pointer which would actually be pointing to the final new created list, and obviously pointer 1 pointing to the first list, pointer 2 pointing to the second list, and the third pointer pointing to in general the list you want to create. And just if you have pointer 1, if you have pointer 2 pointing to these two linked lists, just see which of them is shorter, which of them is smaller in value. If for example you want to compare 2 and 3, then 2 would be smaller. So this linked list, second linked list will get a chance. So just select this particular value and then just move this pointer to the next node, because that would be next under the consideration. But what do I mean by selecting this particular node, or what do I mean by just moving the pointer? That is something that you need to that you need to figure out yourself, and do really attempt these particular questions. They are really worth doing. So what I'll be doing is actually, apart from this particular solution, I'll also post a simple solution which is extra scale solution. So if you have time, first of all, maybe you need to try both the versions. That you can actually just, it's a comparatively easier thing to think that if you actually creating separate copies of each particular node in the linked list, that you can actually think both ways. Obviously, constant space solution would be better, and for practice, you can actually code both the solutions. Both of them will give you separate flavors. This was about operations in linked list, and throughout like before concluding, our discussion was rather like largely one-sided, like advantages of linked lists. So linked lists do pose certain disadvantages as well, and arrays do lead with respect to linked lists in certain areas. So before wrapping up, I just like to explain those particular things. For example, if you want to access a particular node, for example, let me tell you that just take me to the third node in the linked list. So for array, it was just like array and a square bracket in three, and you're actually there. But for linked list, it's not that much easy. You actually just have the access to the first node of the linked list. So you actually have to start from first node, move to the next, move to the second node, then again do the next operation, and then move to the third node. So that is actually in general an order n. That is a linear time operation, whereas in arrays it's a constant time operation. So accessing is quite quick, a quite easy operation in arrays. So whenever you need to compare between arrays and linked lists, just try to see that whether you have plentiful of insertion deletion operations, or you actually have plentiful of excess operations. If you have excess operations more, then prefer arrays, or if you have insertion or deletion operations more, then you can prefer linked lists.